All right, Sam.
Okie doke. Hello, everybody. Thank you for coming. I'm Sam, and I'm going to be talking to you guys about model predictive control for resource-constrained robots, or microcontrollers. And I want to start by saying that I have done a lot of this work with other people in the lab. The main content of this talk is going to be from the paper TinyMPC, which is done with Kai, Anushka, and Alakia, and then Brian and Zach, of course. And this was a cool paper we submitted to ICRA. It ended up getting Best Paper in Automation, which is really exciting. And it wouldn't have been possible without the contributions of everybody involved. So I just wanted to thank them first. So diving in, I just want to talk first about convex optimization, and specifically quadratic programs. Typically, convex quadratic programs consist of some cost function that's quadratic and some constraints that are convex. And this produces a bowl kind of shape. And the reason we want this kind of shape for our optimization problems is that we have nice theory behind them that allows us to solve them very quickly and very robustly. There's guarantees on whether or not we can solve the problem. We know we can solve it sometimes in a specified amount of time, which is really nice. And usually they're just very efficient. And this is great. So we want our solver that we're going to try to produce to have these guarantees as well. And then we can talk about model predictive control. This is kind of just an idea. Model predictive control is just the idea that you solve an optimization problem over and over again very quickly. And you apply the latest control input to your system. And in doing this, you mop up some error in your system or your sensors, et cetera. And you can write model predictive control basically however you want. But one way to do it is as a subset of convex optimization or convex quadratic programs. So you can write this with a quadratic cost. And if we expand this guy out by switching our decision variables, which is just, it was y, now we're switching it to our state, x, and our control inputs, u, for each time step. And if we expand this out, we can write it as this set of stage costs, which we sum up over our time horizon, and then some final cost. And you can add like linear terms in here to take into account like your reference trajectory that you want to track. But this is like the basic form. And then we have some convex constraints in order to keep it a quadratic program. The first thing we have are linear dynamics constraints. And this is important to keep in mind that these are linear dynamics constraints because it'll be one of our limitations later on. But they have to be linear because if they are nonlinear, then they can't be equality constraints in a convex program. So the only convex constraints that are equality have to be linear. And then we have some other linear inequality constraints as well. We can add whatever we want in here, as long as they're convex. Right now, we'll just talk about linear inequality constraints. So these kinds of problems are really nice. We have them one for each time step. These kind of problems are really nice because they allow us to take advantage of sparsity patterns in model predictive control. There's a lot of sparsity in like the structure of the problem when we form this as a QP. And it's nice because there's temporal structure. So between iterations, when we're solving this, the solutions are going to be very similar to each other. And we want to be able to warm start, that's what it's called. We want to be able to warm start the next solution with the previous answer. And this makes it so that we don't have to do as much work every time. We don't have to reset at 0 when we do our next solve. So convex model predictive control has been used a lot in the wild. We've gotten pretty good at using this. We've been able to like make robots walk around, land rockets, drive cars. And even if convex MPC isn't being used at the highest level, it's probably some nonlinear model predictive controller, we can be pretty certain that it's being used to solve some subproblem. Just because of all of the nice properties, it's very robust, very reliable. And so that's cool. We want to use convex MPC. But there's something that all of these robots on the screen have in common, and that is that they're very large. And that means that they're capable of carrying big computers, large computers that are big enough and powerful enough to solve these problems online in real time, at real-time rates, and also have enough memory to store the problem in the first place. And that's not something that can be said for tiny robots. Let's say we want to do the same thing on tiny robots. We want to perform these cool behaviors, super dynamic, subject to complex, constantly changing constraints. The computers that tiny robots can carry are generally constrained to microcontrollers. Sometimes you can fit like a Jetson Nano or something tiny on there, but most of the time, they're not going to be as powerful as the computers that you can store on these massive robots. And this is a problem for two reasons. One, these microcontrollers are pretty slow. And so we just can't solve the problem in real time. And the other is that they generally don't have enough storage in RAM to even store the problem in the first place. So that we're constrained by memory as well. And to compound this issue, these robots, because they're small, the scale is so small, it means they have pretty fast dynamics. And in order to stabilize them, you generally need to solve the problem much faster as well. So not only is it harder to solve the problems, but we need to solve them faster in order to get the timescales correct. And just to give some, I guess, perspective on the kinds of controllers we're working with, I just found some very generic ones. We have an Arduino and an ST microelectronics breakout board here. And these are some pretty common microcontrollers you'll find in the wild. And they run anywhere from like a few tens of megahertz to hundreds of megahertz and have similar amount of kilobytes of RAM. And if we compare this to consumer products like desktops, laptops, these things run with many more cores, each running at gigahertz speed, and then we have gigabytes of RAM. So orders of magnitude difference between these two things, and we're trying to target all the microcontrollers to get these tiny robots to run in real time on board, so we don't have to use some offboard computer and then send over the commands. And there's a lot of ways we could start to formulate this problem. We can look at existing solvers and see what's out there, what people have already done. And there's a lot, it turns out. People have built a lot of solvers for quadratic programs and other types of small problems. OSQP is a pretty common one. This is a fairly standard solver for quadratic programs. We also have some methods that solve quadratic programs using active set methods, interior point methods. We have a lot of these solvers. People have put a lot of time into making these things. And I'll take a few of these out just to show some comparisons. So some things we want out of these are warm starting. We want to be able to use the previous iteration as the start for our next solve. And we want them to be generally have support for embedded systems. So for example, Cosmo is good at warm starting. This actually isn't a QP solver, but it gets the point across. It's good at warm starting, but it isn't really specified for embedded systems. ECOS is specified for embedded systems. It has good support for it. That's what the E stands for, embedded, and actually handles conic constraints, which is cool. And then OSQP is good for both of these things, actually. It uses an ADMM method, which we'll talk about later. So it's nice for warm starting, and it has support for embedded systems as well. But the commonality between these and like most of the other ones on the other page is that they're not tailored for model predictive control. So they're built so that you can solve generic problems. You can put whatever you want in there. And that makes them a little bit more bulky than we want. Too bulky to fit the kinds of problems we want on these tiny microcontrollers. And that's where TinyMPC comes in. This is the solver that we're going to be talking about today that we created to solve this issue. And TinyMPC takes some of the knowledge we have from optimal control and classical control and pairs this with the temporal structure of the model predictive control problem to accelerate and compress the problem. And that just means we're trying to make it faster, and we're trying to reduce the memory footprint of the convex MPC problem. So let's look at the problem in its whole, in its entirety. This is what it is. It's a little much to look at. We're going to be taking a page out of OSQP's book and using the alternating direction method of multipliers. But first, in order to go through this derivation, I just want to make this a little bit more palatable. So the first thing I'm going to do is reduce this formulation down into a more standard quadratic program form, which looks like this, where we have some linear dynamics. And then I'm separating that from the inequalities because we'll pair these out later and use the linear dynamics to play a little trick and make this a lot faster. But this is generally what it looks like. We have some quadratic cost. And if we expand H and G using the formulation for our convex MPC problem, we can see that it has a really nice structure. There's a lot of zeros in here. And most of the solvers that you would put this into, like they have sparse methods and things like that, but they're not going to take full advantage of this structure like we can if we're making a solver for model predictive control. And then G is our dynamics. Those are our linear equality constraints. Okay, and then one more thing to pare this down even farther, I'm going to take these constraints that we just separated and then combine them again into a convex set C to make this derivation a little simpler. And then to solve this problem, ADMM introduces a slack variable, Z. And the slack variable Z moves our constraints from our or our inequality constraints into the cost function. They're contained inside this indicator function, I. And the indicator function just says that if we are violating our constraints, we want to add infinite additional cost to our cost function. And if we're not violating our constraints, we don't want to add any additional cost. And this makes sense intuitively. If we are not inside of our constraint region, we want to penalize it maximally to cause it to go inside the feasible region as quickly as possible. And if we're already satisfying these constraints, then we don't care. We don't want to modify or influence the decision that's being made for minimizing this optimization problem. But mathematically, it looks a little nasty because now we've introduced this discontinuous function. There's like infinities in there, so it looks kind of gross. But it turns out that in the ADMM framework, this actually makes the problem much easier to solve. And the way it's solved is by forming the augmented Lagrangian of this problem. And the augmented Lagrangian has a few terms in it, but it's just the same thing we saw before. We have this cost. This is the same cost function from the previous slide. And then it introduces a few parameters for this penalty. So there's the penalty term rho, and then there's a Lagrange multiplier as well. And these serve to push our primal and slack variables, y and z, closer together so that they're equal to each other at the end of the solution. Okay, the next thing ADMM does is minimize this augmented Lagrangian with respect to our primal, and then it alternates between doing that and minimizing with respect to our slack variable, z. And this is where the alternating direction comes from in ADMM, and the multiplier part comes from the Lagrange multiplier. Once we alternate between these two, in between alternating between these two, we add an additional update on our lambda term. And this is a gradient ascent step, and this turns into our 3-step update rule. So we have our primal update, slack, and dual. And looking at the time complexity for these, the dual update is just vector addition. So this turns into O of n. It scales linearly with the size of the problem. The slack update is generally a projection onto the feasible region. So that's O of n squared if you're doing like linear projection. In the case of clamping or bound constraints, this can just be O of n, which is kind of nice. And the primal update is O of n cubed because it is the solution to a system of linear equations. And so it involves a matrix inverse, and a lot of time must be spent in this step. So this is the bottleneck for our system, and we would like to minimize that bottleneck as much as possible. So let's take a look at the primal update a little bit closer, and see what we can do. The first thing we see is that we're minimizing with respect to the primal, which is y, and that means that our z and lambda, our slack and dual, are constant. So if we look at the augmented Lagrangian again, with only respect to y, that means our indicator function, which only relies on z, just drops out of the picture. We don't care about it anymore. And to solve this problem, all we have to do is take the gradient, set it equal to 0, and then rearrange the terms to solve for y. And we can immediately see the culprit of our O of n cubed time complexity is this inverse right here. But we can also notice that this is the solution to the unconstrained problem of our minimization of our optimization problem we had earlier. So it looks like a little bit like this. There's a little different because we have the row in there, so we have to scale some things, but essentially it looks the same. But we can't really do much with this. So what we're going to do, we're just going to decide to do this, is take the linear dynamics, the equality constraints from our slack update. So our slack update was handling all of the constraint feasibility. We're going to take it from the slack and give responsibility of satisfying those linear dynamics to the primal update. And if we do that, we just throw it in there. What we get is this quadratic cost, this linear dynamics, where H and G are defined by those sparse matrices we saw earlier. And then if we expand that out, again, we get this nice temporal structure. And this looks exactly like a linear quadratic regulator with linear dynamics, quadratic cost. And this is really nice for us because we know how to solve this problem. This is the solution. This update step at the bottom here is the solution to Riccati recursion. And it's in the form of an optimal gain matrix K and a feed-forward term lowercase d. And if we look a little bit farther into the Riccati recursion, because now we want to move on from the primal update, that's the new primal update that we're going to use, so we have to minimize this Riccati recursion complexity as much as possible. We see that Riccati recursion also gives us a few more matrices. It gives us this capital P, which is a cost to go Hessian, and it gives us the gradient term of that Hessian, which is lowercase p. And it gives us one of these for each time step in the horizon. So you can see that this is already going to be a lot of matrices to store if we're trying to store these online. And in addition, these are pretty complex variables to compute. This is all the math for the Riccati recursion. You do this for the entire horizon, and it has matrix inverses and matrix multiplication, and it's generally expensive. So we haven't really done anything yet. We've just kind of rewritten our problem, our primal update, as this Riccati recursion, and it's still expensive. So we want to reduce this as much as possible. And the first thing we do is to get rid of some of this extra memory that we're storing, or to reduce the memory we're using as much as possible, is to use the infinite horizon LQR problem instead of the finite horizon, which is what this is describing. And the way we do that is offline. We cycle between solving for K and P over and over again. And we can do this because we're using a constant dynamics, a linear dynamics. So we know A and B, we know Q and R because those are in our cost function. And so we're cycling between K and P until they converge to the solution of the infinite horizon LQR problem. And that's just a single matrix K infinity and a single matrix P infinity. And now that we have this, we can plug them into our linear terms. And we can see that we also know a lot of these terms as well. We know A and B, we know R. And so we can just single out this matrix inverse and a few of these matrix products. And we can pre-compute them because we're already pre-computing the K infinity and P infinity, might as well do more. We can pre-compute these guys offline. And then online, we just have matrix vector products to compute. And so this becomes O of n squared. This is our backwards pass, which is what we're going to refer to it as. And then in the forward pass, you can use that LQR policy along with the linear dynamics to roll out your decision variables. And so now this is our new primal update. It's O of n squared. We've reduced the computational complexity by doing some pre-computation. And now we can take a step back and get some perspective on what we've done by looking at the full algorithm. So offline, we just pre-compute a few of these matrices. And then online, we cycle through the primal, slack, and dual update steps until we converge. And one additional thing is that we are using, this right here is assuming that we're using a single parameter, single value for rho, our penalty parameter. But in reality, what we're doing is choosing a few different values for that penalty parameter, and then switching between them online when necessary in order to speed up the rate of convergence. And each different penalty parameter comes with its own set of pre-computed values. So we have a few more of these guys in the background, and then we're switching between them. And this doesn't introduce too much overhead since there's only 4 matrices to compute. Okay, so let's throw this on a microcontroller and do some benchmarking. We compared a TinyMPC against OSQP, which it's based off of, on a TinyMPC 4.1 running various randomly generated model predictive control problems. The TinyMPC 4.1 is a pretty powerful microcontroller, and we chose this because we just wanted to get more data, and we knew that the like OSQP would take up a lot of RAM, so we wanted something with a little bit extra. And we're varying the state input and horizon, so we have a few different plots. But this is what it looks like for the memory results. OSQP obviously uses a lot more memory than TinyMPC. It makes sense. It's not built to specifically solve this problem, and TinyMPC is, so it's able to make more efficient use of its memory. And we can see that OSQP is violating the memory constraints of the microcontroller at a horizon of around 30, while TinyMPC clearly can store much larger problems. But that doesn't really mean much if we can't solve it faster. Luckily, we can. It ends up that we can solve the problem about an order of magnitude faster than OSQP at the peak. And this is nice. So we know we can solve larger problems. We can store them on the microcontroller, and we can also solve them in real time, at real-time rates, and allow us to do optimal control. So this is cool. Let's put it on a real robot. We chose the Crazyflie 2.1. This is a tiny quadrotor. It fits in the palm of my hand. It weighs about 27 grams, which, like I said before, this is very small scale. And 27 grams is super light, so this has very fast dynamics, which means you need to solve the problem pretty quick. And luckily, we can do that with TinyMPC. Additionally, this doesn't have nearly as much RAM as the TinyMPC. There's some overhead and stuff that goes on. So we are able to fit, like, I think we're using horizons of like 30 to 40 on this guy for various different things, but we change them for the different problems we're solving. And then this has a state of 12 state variables, defining like a point mass with an orientation. And then we have 4 control variables, 1 for each thrust or 1 for each rotor. And so we compared TinyMPC on a few different tests. One is this figure 8, and we compared against a few of the other built-in controllers. And TinyMPC is the only one able to reason about the torque limits or the thrust limits and generate a decent looking figure eight. And the reason it's not perfect is because this figure eight reference trajectory is actually way too fast. It's a 3-second period. So even if you had like the perfect controller, this still wouldn't be able to track it. So TinyMPC does a pretty good job. We additionally tested against the same controllers on an extreme recovery task. So starting the drone at 90 degrees, and then having it fly off and trying to recover. And again, TinyMPC is the only one able to reason about the torque limits and generate a decent looking recovery. PID is actually able to recover. It just looks kind of crazy. So that's exciting to see that TinyMPC can do it so well. And then to test bound constraints, we flew the drone back and forth, took a long exposure photo. And this is what that looks like with the lights. And then we just set some constraints on the state and flew the same reference trajectory and noticed that it is not violating those constraints. So we showed that we can put bound constraints on the system. We can put bound constraints on the inputs. We can put bound constraints on the state. But what if we want to do something more interesting? What if we want to add cone constraints and like linear constraints like we had written down before, or hyperplane projections, linear constraints, I guess. So you can do a lot with these things. You can do like the rocket landing problem with a thrust cone. You can have an attitude constraint on your drone. You can have like reason about friction cones on robots. And it's really nice that we're using the ADMM method because it lends itself to adding these constraints very easily. If we look back at the 3-step update we had before and single out the Slack update, this is what's handling almost all of the constraints, except for the dynamics constraints, which we gave to the primal update. And so we can just set whatever projection function we want in here as long as it's convex. It'll end up converging for the most part. And Slack update, for now, what we've been using is just this clamping operator. So our convex set has just been some max and min on our decision variables, and we just clamp it to that region. But if we want to put like hyperplane projections, which is just taking a plane in an arbitrary dimension and projecting a point onto it, like an inequality constraint, then we can just write it down, throw it in our Slack update, and then put it on the robot. And so in this example, we have the drone sitting at the origin, and we have this point mass, this point with an inflated sphere around it to act as like a keep out zone. And it is the drone's trying to save the origin, and the point mass is trying to follow the drone, chase it around. And each of these green planes that you see are a linearization that's like part of the hyperplane. And it's separating the space into the 3D space into a half space, which the drone must stay in at every time step. And it's like doing a little bit more fancy stuff by like projecting the location of the sphere at every time. But it's really, it produces some nice behaviors. And then we can just throw this on the real robot. So we did that. We have a stick getting motion capture data of the end of it. And we inflated the sphere so that, it's similar to the transparent sphere in the previous example. And we're able to generate some cool behaviors. So what if we also want to do second order cones? Second order cones are commonly approximated by linear inequality constraints. And like this is generally, like it works for the most part, but there's a few problems. Like one, if you have too many inequality constraints, if you have more inequality constraints, you're approximating a better cone, but then it takes longer to reason about this problem. And if you have too few, or regardless of how many you have, really, you're going to be making approximations. This will be conservative, and you'll have some bias leading towards the corners of the cones and whatnot. So it's better to just be able to write down the second order cone problem in this entirety, which we can do. We can just write it down, throw it in the Slack update, and then this becomes our new Slack update. And we can even like compose these, which is nice. We can compose like hyperplane projections to Slack update as well as cones. This is an example of the Crazyflie just flying in a helical descent trajectory. I'm not going to play the whole thing, but if you run this out and take a long exposure photo, this is what it looks like. And let's say we want to add a cone to this. So we threw one in the origin. This is generally considered a glide slope constraint, and ran the drone in the same helical pattern. And what ends up happening when you constrain it to this cone is you create a nice like ice cream cone looking shape. And yeah, that's pretty exciting to see that works so well. So some limitations for TinyMPC. The biggest one is that we are using a single linearization. So we have one AX plus BU. And that makes it so that we can't do things like backflips or like barrel rolls, things that go crazy far outside of the linearization. But we just showed that we can also recover from a 90-degree angle. So you can clearly take this pretty far. And it's not too hard to imagine linearizing about a few different orientations or attitudes, at least for the drone, and then switching between them intelligently online in order to get some nice nonlinear behavior. And then for like multi-body systems, it might be a little harder because there's maybe less region of attraction there, but the general idea stands. And then before I end, I want to talk about the some of the work we did in making this accessible. We created a code generation platform. Platform is a strong word. It's really just like an interface for C++ and Python where you can generate code, C++ code, that will go onto microcontrollers pretty easily. And the Python interface actually has a module built in for generating a new module from that generated C++ code, and you can call that in whatever interface or whatever pipeline you already have set up. So say you have like a vision process going and like a state estimator happening or a planner, you can just throw in the generated code from these interfaces, or you can just use the Python interface directly. And I think that's been pretty helpful. A few other people from different schools have reached out and asked if they can use TinyMPC or asked for help using TinyMPC. BitCray has asked us to do a blog post about TinyMPC, which is cool. Someone wanted to do a perching behavior. It's in the top right, which worked really well. Ari from CU Boulder wants to use TinyMPC on his tiny quadruped. This thing's like really small, smaller than the Crazyflie. He wants to do like obstacle avoidance, things like that. And then some friends from UC Berkeley have been using it in their simulator for embedded systems, which has been really cool to see. And that's all I have. I want to say thank you to all the people who have helped me on the project. Thank you to my advisory committee, Zach, Aaron, and Brady. And thank you to Brian for being a great mentor and just a great person in general. And thank you to everybody in the lab. It's been cool to hang out with. Yeah, that's all I got.